Marhaba. Okay, in this session we want to prove one part of the fundamental theorem of arithmetic, which says that the prime factorization of a positive integer is unique. Okay, but before we do this, we need to prove a very important theorem regarding prime numbers. Okay, so what is this? Before stating what is this lemma about prime numbers, let me give just a particular example. So let's look at this example. Now the integer 6 divides the product of 8 times 3, right? Because 8 times 3 is 24 and 6 divides 24, since there is an integer k such that k times 6 is 24 and this k is 4, right? 4 times 6 is 24, 6 divides 24, and so 6 divides 8 times 3. But look, but 6 does not divide 8 and 6 does not divide 3. You see what is this example is about, that we have an integer which divides the product of two integers, but this integer does not divide each of the integers, both integers. So it doesn't divide 6, it doesn't divide 3, but it divides their product. We will see that this can't happen when this number is a prime number. Okay, so let me state the lemma. So lemma, it's a very important property about prime numbers. The lemma says that let a and b be positive integers and let p be a prime. Then if p divides the product, then p must divide one of them. Then either p divides a or p divides b. Okay, so this is a very important property about prime numbers, that if a prime number divides a product of integers, then this prime number must divide either a or b, or maybe both. Okay. So let's prove it. Okay, if so, case 1, suppose p divides a, right? If p divides, before I start with the cases, okay, we want to use a direct proof. So we assume the hypothesis, we want to show the conclusion. So let's suppose the hypothesis. So suppose p divides a times b. Okay, thus by definition of divisibility, there is k in the integers. Okay, such that what? Such that AB is equal to k times p. Okay, so we know this. We know that AB is equal to k times p because we assume that p divides the product. Now we need to show either p divides a or p divides b. One of them must be true. So case 1, suppose p divides a. If p divides a, then p divides a or p divides b is true. So we're done. Okay, now case 2, suppose p, the prime, does not divide a. And in this case, we will show that it will divide b. Okay, you see the strategy here? We assume this, that p divides the product, and then we want to show that either one of these must be true. If p divides a is true, we're done. If not, we need to show that the other one must be true. So now we are in case 2, p doesn't divide a, so we need to show p divides b. Now look, what can we get from this, that p does not divide a? We know that p is a prime. So the only divisors of P are 1 and P. So what can you tell me about the GCD of P and A? What is the GCD? The GCD is the greatest common divisor. But the only divisors of P are 1 or P. So this means that the common divisors of P and A are either 1 or P. But P cannot be a common divisor because it doesn't, okay, P divides itself, but it doesn't divide A because we are in case 2. So P is not a common divisor. This means that there is only one common divisor between P and A, which is 1. And it will, since it's the only common divisor, it is the greatest. So the GCD of P and A is 1. Remember, so P and A are co-prime. If you remember, we defined two integers to be co-prime if the GCD is 1. Okay, so now we know that GCD of P and A is 1 by Bezout's theorem. We know that the GCD of any two integers is a linear combination of the two integers. So by Bezout's theorem, there are S and T in the integers such that what? Such that the GCD of P and A is 1. So such that the GCD is equal to S times P plus T times A. We know that the GCD of any two integers is a linear combination of the two integers. But we've seen that since P doesn't divide A, then the GCD must be 1. And 1 is equal to SP plus TA. So we know this, and we want to use our knowledge that AB is equal to KP, that P divides the product. So let's create AB in this equation. Here's an A, it remains to multiply the whole equation by B. So 1 times B is B, SPB plus TAB. And this means that B is equal to SPB plus T. We know that AB, P divides AB, and AB is equal to K times P, right? And this means that, so this implies this, and this implies this, and the last equation implies this equation, that B is equal to SPB plus TKP, and we see that we can take P as a common factor, so B is equal to SB plus TK, where P is a common factor, and this means that B is equal to some integer L times P. What can you deduce? Since B is equal to an integer times P, by definition of divisibility, this means that P divides P. And this is the end of the proof. This is what is desired. Okay, so again, what is the theorem? That if P is a prime and it divides the product, then it should divide A or B. This is a very important property about primes. So here P is a prime. You can check, for example, 5 divides 10 times 15, since 5 divides 150, and you see that 5 divides 10 and 5 divides 50. Okay, this will always hold since when P is a prime. Okay, now use induction. So this is an exercise for you. Use induction on the number of terms in the product. So use induction to prove the following generalization of the lemma. So let's call it. So what is the lemma? If a prime p divides a product of integers, any number of integers, a product of integers, then p divides one of them, one of the integers. One of the integers. Of these integers, okay. In symbols, if p divides the product of, say, a1 times a2 times a3 up to an, so these are all integers. If a prime divides the product of n integers, then p divides the first one, or it divides the second one, or it divides the third one, and so on, or p divides the last one. Okay, so you prove this by induction on n. When you start with n is equal to 2, for example, when n is equal to 2, then it is the theorem we proved above. If p divides a1 times a2, then p divides a1 or p divides a2. And then you assume it's true for n and show it's true for n plus 1. Okay. Now we will use this lemma to finish the proof of the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic, what does it say? Remember, it says that every positive integer can be written uniquely as a product of primes. Okay, can be written uniquely as product of primes. Okay, so there are two parts of this theorem: that it can be written in the first place as product of primes, and the second thing, that this expression as product of prime is unique, which means any two expressions of the same number, positive integers, contain the same primes. Okay, so this was proved. Can be written as product of primes was proved by strong induction. We did this already, and so it remains to show that the product is unique. Okay, so let's write this as a theorem. So the theorem says that the prime factorization, okay, the prime factorization of any positive integer is unique. Okay, so we want to prove this, and we will prove it by contradiction. Okay, so prove. So look at the logical form of the statement. For any positive integer, its prime factorization is unique. So for the sake of contradiction, suppose it's false. For contradiction, suppose the statement of the theorem is false, which means not every positive integer has a unique prime factorization, which means there exists at least one integer with two different prime factorization. Okay, so for contradiction, suppose there is n, which is a positive integer with two different product of primes. Okay, prime factorization. factorizations. Okay, say that we have n is equal to, say, to the prime p1 times the prime p2 up to the prime s, and then I want to say the prime p prime 1, p prime 2, I'll tell you why, up to the prime k, say, prime. So this is the first prime factorization of n, and the second as a product of primes, and the second one is q1 times q2, okay, up to qt, times, say, p1 prime, p2 prime, up to pk prime. So all what I'm saying is that we have two prime factorizations of n. This is the first one, as we express n as a product of primes, and there's another way to express n as a product of primes, and we just listed the primes which are common in the two prime factorization. So this is factorization number 1, and this is factorization number 2, and they are different, but maybe they have some common primes. Okay, so these are, say, we have k many primes here which are also exist in this prime factorization. Okay, so what we will do is that we will divide this equation by p1 prime, so p1 prime will be cancelled, p2 prime will be cancelled, and so on. So we just cancel all the common primes from both sides. So this means we will end up with this equation that p1 times p2 up to ps is equal to q1 q2 up to qt. And what do we know about these? No primes in common, okay, because we removed all the common primes. So no primes in common. Remember, we are hoping to get a contradiction. Okay, and notice that both s and t must be bigger than or equal to 1, because, say, if there were no primes here, then we will see that this will not be an equality. We'll get a prime here equal to 1, and no prime is equal to 1. Like some of the qi's will be equal, the product of the primes here will be equal to 1, and we know that the least prime is 2. You can check that this must be the case. Okay, so we have primes here and we have primes here. Okay, now you can write this equation as p1 times p2 up to ps is equal to q1 q2 up to qt. Okay, but the product of primes is an integer, so this is, say, p1 times l is equal to this integer. This means that p1 divides this number, right? Because this number is equal to some integers times p1, but since p1 is a prime, okay, now we apply our previous lemma that if a prime divides the product of integers, then it must divide one of them. So by our lemma, by the property of primes, that this means that p1 divides q1, or p1 divides q2, or p1 divides the last one, qt. Okay, so say p1 divides qi, I don't know, for I is between t and 1. But look now, what do you know about p1 and qi? Both of them are primes. What does it mean that a prime divides another prime? Qi is a prime, which means the only divisors of Qi, so the only divisors of Qi, since Qi is a prime, are 1 and Qi. But P1 is a divisor of Qi, but P1 is also a prime, so P1 can't be 1, because since P1 is bigger than or equal to 2, it's a prime, we have that P1 must be Qi. Okay? We have that P1 is equal to Qi. And this is a contradiction. Why it's a contradiction? Because, look here, we assume that this factorization has no prime in common with this one, but we found out that P1 is equal to some Qi here. One of the Qi's from Q1 to Qt is equal to P1, and this contradicts that these two expressions have no primes in common. We already removed all the common primes. Okay, so this is a contradiction. So we have a contradiction, and this means that the statement of the theorem is true, that every positive integer has a unique prime factorization, and this finishes the proof of our fundamental theorem of arithmetic, which says that, okay, let me just this is the fundamental theorem of arithmetic. Again, it says that every positive integer can be written uniquely as product of primes.